Um, so the first thing that I would like to touch base upon is the key concept of the related to quadratics and domain and range. So first, quadratics key concepts that we had done in our previous year. So as far as quadratics is concerned, obviously you should be really good with the forms of the quadratic, the concept of discriminant, and inverting. So these are the three areas that a lot of times you will get the challenge. So just to begin up with, now we have got the three standard forms that we are doing, which is the first one is a factored form, ax minus b, x minus q. Second is the ax squared plus bx plus c form, which is your standard form. And the third one is the perfect squared form, just reminding about what does each quantity stand for. So obviously here, you know that P and Q stand for the roots. P and Q stand for the roots. Certain critical stuff that you need is like if your A is positive, you know that's a happy phase graph. If A is negative, it's a sad phase graph. These all will be very helpful while you're doing Sine diagram. Like for example, if you have to do the Sine diagram, like k squared minus 3k plus 2 less than 0, then you're going to basically take the roots of this, which is like your 1 and 2, and put these numbers on the number line, and then you look at the coefficient of x squared. If coefficient of x squared or k squared is positive, it will be a happy phase graph. So it's very quick tool to solve the inequality, obviously, as we know. So here we got negative, positive, and here we got positive. So these are the very important things that we need to know as at the ground, ground root level. So here the correct answer will be x greater than 2 or x less than, sorry, this is x greater than or equals to 1 and less than or equals to 2. So that's going to be the answer for this particular inequality. Now what is more interesting is that when we do the domain and range, you will get across a lot of Sine diagram quadratic inequalities. So we should be good with that. Just to remind you, something very interesting, which is about the ax squared plus bx plus c. As we know, x is minus b over 2a, that's a line of symmetry. Okay, and what is really important is understanding the key concept related to the roots. So if you have negative b plus or minus root b square minus 4ac upon 2a, just a reminder that these are the two roots where the graph cut x-axis. So one of the root will be with plus, other root will be with minus. Now sometimes you're expected to know this distance, like how much is this distance, and the distance is obviously the difference in the root. So if I this x1, this is x2. If you subtract x2 minus x1, you're going to get this distance. Obviously, you subtract this. So if you subtract, let's say negative b or plus root b square minus 4ac upon 2a minus the second root, which will become plus b upon 2a, and this will become again this will become plus root b square minus 4ac. So this get cancelled and you'll get the distance between the roots as 2 root b square minus 4ac upon 2a, and this 2 and 2 get cancelled. So you get the distance between the roots is this. So sometimes you might be asked to calculate what's the maximum separation between the roots and all. In that case, you are supposed to do this. Another interesting thing is obviously like your knowledge about the line of symmetry. A lot of times in more of the standard level question, what they give is that they're going to give us a standard parabola, ax squared plus bx plus c. They're just going to give a table. Okay, so they're going to give the table. They're going to give the signs. So let's say these are the quantities a, b, c, and let's say b square minus 4ac. And they'll say, okay, so here's a graph. Let's say this is a graph, and for this graph, you predict the signs of a, b, c, and so is b square minus 4ac. Of course, pretty simple that you know that C is the y-intercept. So if you see the y-intercept is negative here, so this is negative here. It's pretty easy to say A is going to be negative because it's the upside down parabola. Then B value is something that troubles a lot of students, and the B square minus 4AC. So when you're talking about the B square minus 4AC value, so B square minus 4AC is basically your discriminant, which is like you can see clearly that if B square minus 4AC is greater than 0, it is cutting at two distinct points. If it is B square minus 4AC, it is less than 0. It never touches the graph. So in this case, your graph is either above x-axis or below x-axis. So if your B square minus 4AC is entirely above x-axis, this is the case for two distinct roots. If it is entirely above x-axis, like this. If it's entirely below x-axis, like this. So in both these cases, your B square minus 4AC is going to be less than 0. So here, of course, we can see that since it's cut, the graph is cutting at two distinct points. So graph is cutting here at two distinct points. You can see here and here. Hence, it will have discriminant positive. Now, the only concern is that the sign of the B value. The only problem is the sign of the B value. Now, if you find the sign of the B value, actually, if you look at the line of symmetry here, line of symmetry is having a negative value. So it's like some negative equation you have. So what you do is, when you're calculating the line of symmetry, it is basically x is minus b upon 2a. Now, since you know a is negative already, this negative cancel. So if in order to have the line of symmetry toward the negative side, your b must be negative. So that's how b must be negative here as well. So this is what this is like some of the basic, I would say, skill builders that you need for the quadratic. And of course, like the next part is your sum of the roots and product of the roots for quadratic. Now, when you're doing sum of the roots and product of the roots for any particular quadratic equation, as we know that the general backbone for any quadratic is x squared minus sum of the roots times x plus product of the roots. So this is the general backbone in case if you know the roots of the quadratic and you want to form the quadratic. Like for example, if roots are like 2 and 3, the quadratic is going to be x squared minus 5x plus 6. So it's pretty simple to form the roots from the quadratic if the roots are given. Now, second thing is that if you have been given like a question where you're expected to know this concept of sum of the roots and product of the roots. Now, if I express a quadratic ax squared plus bx plus c in form of sum of the roots, product of the roots criteria, then remember that the sum of the roots and product of the root is basically minus b over a and alpha times beta, which is product of the root, which is c over a for any given standard quadratic. Now, the use of this, obviously, we all know that, but just touching base upon. Okay, so suppose if you got a quadratic, let's say 2x squared minus x plus 5. Now, this is a quadratic whose roots are, let's say, alpha and beta. And you got to find another quadratic whose roots are alpha square and beta square or some other stuff, but without finding the value of alpha and beta. So since we already know the background, the way you prepare a quadratic equation. So if you got x squared minus sum of the roots times x, sum of roots times x here plus product of the roots. So x squared minus sum, it will become alpha squared plus beta squared times x plus alpha squared beta squared. Now, alpha squared plus beta squared is basically we need to find out. So we know that this is alpha plus beta the whole square minus 2 alpha beta. So alpha plus beta, if you see here, is minus b over a. So if I find that out first, so my alpha plus beta value here is minus b over a, which is negative 1 upon 2. Will become positive 1 upon 2, and alpha into beta is 5 upon 2. Just put that value here, so it will become half the whole square, or minus 2 times alpha times beta, which is 5 over 2. So it's 1/4 minus 5, which is negative 19 over 4. So the alpha square plus beta square value is this, negative 19 by 4. And then we have got the quadratic backbone. So you just substitute the values, so it will become 19 by 4 times x, because this is negative 19 over 4, minus becomes positive. And then you got alpha square plus beta square, which is basically 5 over 2 square, which is 25 over 4. So this is the general quadratic that I wanted. Of course, you can linearize with just taking the coefficients as 4x squared plus 19x plus 25 as the general quadratic. So this will be the quadratic where you have the basically the roots will be square of the previous roots. So this is the general information that you need. And I think one of the skill that is a lot of students still get confused with is the concept of inversion for a quadratic and concept of writing into perfect square. So a lot of times we get hiccups when you're writing into perfect square form. So if you got, let's say, something like negative 2x squared plus 8x plus 7, and I wanted to write down this in perfect square form. Now remember that to write in perfect square form, it means that it is ax minus h the whole squared plus k format. So you're going to take coefficient of x squared always common first, so it'll become x squared minus 4x plus 7, and then become negative 2, x squared minus 4x. Divide the coefficient of x by 2 to get the b value, so it'll become 4 divided by 2 is 2, so the b value is basically 2. So add the square of that, because you need a square minus 2ab plus b square, which will be 4, then minus 4 plus 7. So you get negative 2 x minus 2 the whole square plus 8 plus 7. So you get negative 2 x minus 2 the whole square and plus 15. So that's your perfect square form. So negative 2 x minus 2 the whole square plus 15. Now, what is really important is that you need to understand the vertex coordinates, minimum, maximum within seconds. If you're an HL student, you need to make sure that you are critically understanding how to find out the maximum value, minimum value without much of the effort. So if I look at the graphing part of this, the vertex is at 2, 15. So vertex at 2, 15 here. And then it is going to be downwards facing parabola. And you get the minimum value of this as maximum value is 2, 15. So this is about the perfect square. I repeat again the steps. Negative 2, I took common just to make sure that the coefficient of x squared is 1, so that I can get b value easily. You got a squared minus 2ab plus b squared. Since I'm adding plus b squared, I'm subtracting here as well, just to make sure that the consistency is obtained. And if you open up the brackets, so these three terms are this, and negative 2 times negative 4 become positive 8 and plus 7. So at least this shouldn't be a problem. And now comes this the last part where a lot of confusion happened with the inverting. So taking the same example, now first thing is that remember that, as we all know, inverse of any particular function won't exist until the function is one-to-one function. Now, if the function is one-to-one, you can find the inverse. Now, when I talk about one-to-one, it simply means that it should pass the horizontal line test. Now, when it is horizontal line test, it means that if you draw a horizontal line, it should not cut the graph at more than a point. So here you can see it is cutting at 2 points. This graph is cutting at 2 points here, if I draw any horizontal line. So what happens is, in such cases, obviously, we restrict the domain. So to get the largest domain, we cut around the left of the vertex or right of the vertex. So I either take this side of the graph, the pink one, or I can retain the green side, any of the choices here. But in exams, you'll get to see that, okay, they'll say, okay, x greater than a, such that it is the largest domain. Obviously, I could restrict it from here onwards. I can take only this part of the graph, but it won't be the largest domain. You're actually unnecessarily removing this domain there. So if you stick from here, your function is still one-to-one. So for example, if my function was something like this, let's say here, the function is still one-to-one function. So in that case, if you wanted to find out the inverse of this function, you could just use this perfect square form, which is like, for example, it will be y equals to negative 2, x minus 2 the whole square plus 15. So if you wanted to find out the inverse of this, it is you interchange x with y, y minus 2 the whole square plus 15. Then you make y the subjects, will be y minus 2 the whole square is x minus 15 upon negative 2. Then you take the square root, it will be plus or minus. This disappears, and then you add 2 to the other side. So your final inverse step is going to be basically 2 plus or minus. So this is going to be the inverse of this function. So 2 plus or minus root of 15 minus x upon 2 you can write, or you can do the other way around. Now, what is really important here is that out of the plus and minus, which one do we take is basically a question mark. So a lot of times, if you simply look at this inverse of this graph, maybe here, I haven't drawn it with the correct proportionality, but according to image, what I have got, if it is y equals to, I reflect in y equals to x line, the graph is something like here. And in common sense, like whenever you have a function here, okay, in the case of, if you took the right side of the parabola, then in that case, you will be taking positive. So if I restricted the left side of the vertex, in that case, I'll be taking the positive. If I restricted the right side, means if I restricted this side, in that case, I'm going to take negative. So this is about the general information about finding out the inverse of a quadratic. Now, we could find the inverse also by a simple, like, let's say if my function was this, y equals to negative 2x squared plus 8x plus 7. You could also do by quadratic formula itself. So if you have got, let's say, x is negative 2y squared plus 8y plus 7, bringing everything one side to the left. So 8x squared minus 8y, 2y squared minus 8y plus x minus 7 equals to 0. Then you can apply the quadratic formula. So y will be negative b, which will be 8 plus or minus root of 64 minus 4 times 2 times x minus 7 upon 2 times 2, which is 4. So you can basically write down this the same inverse in a little different format. Of course, if you simplify, you get the same answer. So it's like 64 minus 8 times x minus 7 upon 4. Of course, you can see that I could factor out 4 and you can simplify this further. So you can see that like these are multiple approaches which you need to know, need to be very confident about while you're finding out the inverse of any particular quadratic. Now let us take some particular sums which can help us solidify our understanding. So for the first question, as a practice, we have the question which is y equals to mx plus 5. It is tangent to the parabola y equals to 4 minus x squared. Now, just to remind you that if there are two curves which do not meet, and like if you solve the equation simultaneously, once you get the resulting quadratic after you equate both the functions or solve for them, you'll note that b square minus 4ac in such case will be less than 0 because they will never meet. So there is no solution. If it is other way around, if it's like touching base upon this thing, you're gonna have b square minus 4ac equals to 0. If it is cutting at two distinct points, in that case, b square minus 4ac should be greater than 0. Now here, this is a tangent. Now it will become y equals to mx plus 5. So it becomes 4 minus x squared should be equals to mx plus 5. So I'm just going to take this equation and solve it. Bring everything to the right side. So get x squared plus mx plus 1 equals to 0. And then you get b square minus 4ac and equals to 0. So you get m squared minus 4 times 1 times 1 equals to 0. You get m squared equals to 4. You get m as plus or minus 2. Next up is where there is a quadratic, which is f of x as x squared plus 2 minus k times x plus k squared. And to find the range of k values for which the function f of x is greater than 0. Now, when you look at the function is greater than 0, basically you got the discriminant. So the function is above x-axis entirely. The discriminant is basically less than 0 for this. So you'll do 2 minus k the whole square minus 4 times 1 times k square less than 0. So we get 4 to minus 2k minus 4k plus k square minus 4k square less than 0. So if you bring it everything to the right side, you get 3k square plus 4k and minus 4 greater than 0. Now you have to factorize this. So like product of the numbers is negative 12 and sum is positive 4. So 6 and 2. So 3k square plus 6k minus 2k minus 4 greater than 0. Factor it out, 3k. Basically, this is going to be k plus 2 and minus 2k plus 2 greater than 0. K plus 2 or 3k minus 2 greater than 0. So you just draw the Sine diagram, negative 2 and 2/3. Here it is negative, positive, and positive. So you want more than 0, so it's positive here and positive here. So you take k is greater than 2/3 or k is less than negative 2. So this is the final answer for this particular question. So in this question, we have basically the quadratic is x squared minus kx plus k plus 1, where it is given that sum of the squares of the roots is 13. You have to find the value of k. So firstly, since sum of the roots is minus b over a, which is minus k upon 1, so it is k, and product of the root is c over a, which is k plus 1 upon 1, so it is k plus 1. So now, if you just apply the formula, we have got alpha plus beta the whole square is alpha square plus beta square plus 2 alpha beta. So if I move 2 alpha beta to the other side, I get alpha plus beta the whole square minus 2 alpha beta equals to alpha square plus beta square. Now this is 13, so put this as 13. Alpha plus beta the whole square is positive k. So k square minus 2 times k plus 1 equals to 13. So if you open it up, we get k square minus 2k minus 2 minus 13 equals to 0. So you get k squared minus 2k. This is minus 2k minus 11 equals to 0. And then you can solve particularly the value of k. So this is actually minus 15. So you solve for k square minus 2k minus 15 equals to 0. So you get k as negative positive 5 or k as negative 3. So I'm generally understanding about the domain and range actually decides the liking for the entire topic itself. So understand there are certain tricks by which we can, master this. So I'm going to actually reveal those tricks and try to explain this particular topic. So first thing is that you should know certain basic graphs. Like you should know the basic functions like the parabola y equals to x squared, we all know. Then you should know the basic graphs of 1 by x function. Then you should obviously know the absolute value function. You should know the equation of circle. And then you should know basically the x cube graph, basic x cube graph. You should know the exponential graphs like a raised to x graph, which is here for a greater than 1. And the log graph is out here, the log x function. I'm going to first talk about the basic principles of the logarithm and the square root functions and all. So in order to actually talk about domain, we all know that domain is the input, a domain is the possible x value, and range is the possible output, or like you can say the y value. So now obviously like when you talk about the possible x value, now it is very interesting to know for each kind of function how do we tackle. So now, for example, if my function is a square root function, let's say square root of some function which is inside, obviously the square root function is only defined for the positive values. So that's how you fix up the domain. Now, for example, if you got x squared minus 16, let's say, and here will be x squared minus 16, obviously greater than or equals to 0. You get the roots as -4 and +4, with negative here, positive here, and positive here. So your domain for this will be x greater than or equals to 4, or x less than or equals to, let's say, -4. Now, second is like, if you have got a function, let's say log function, let's say log of any function here. Let's log of function to the certain base g of x also. F of x and g of x both must be greater than 0 firstly. And remember that g of x even can't be 1. So because the common sense is if g of x is 1, then it becomes undefined. So it's very important to remember this. And of course, we have got the rational functions. Now, rational function is basically if you got a function in denominator, the denominator should not be 0. So that's the criteria. And obviously, you should take care of the concept of poles in case of the common factor. And we'll just talk a little bit in detail in the example now. One of the questions that was there in the exam was like log, let's say, x squared minus 4x. You have to find out the domain for log x squared minus 4x to the base 3 plus square root of 25 minus x squared. Now, this is an interesting question because you have two different domains to deal with. So in such case, obviously, we know that x squared minus 4x must be greater than 0. And if you get, let's say, 0 and 4 as the root, here it will be positive, and here it will be positive because of the happy face. And here it is negative. So the domain for this, actually, if I put on the number line, is less than 0 and obviously greater than 4. So here is 4. Now, if I find the domain for the next one, 25 minus x squared, obviously it is going to be greater than 0. Obviously, it is here will be -5 and +5. It is positive here, it is negative here, negative here. So in this case, your domain is, let's say, -5 until 5. So your domain for this graph, this function is, I'll just take a different color, the -5 until 5. Now, remember that if you have been given a multiple function and you have to find a domain for them, inverse will or like the domain for which both the functions will be defined with the domain for the resulting function. So this is the common domain that you see in both the functions here and here. So this is the only common domain that we see in both the functions. So this becomes the domain for the this particular applied function. So here in this case, the domain is going to be x between -5 inclusive until 0 and 4, basically 4 and until 5. So this is going to be the domain of, obviously, if you wish to write in the set notation, then that's the union. So this is the like common domain procedure. Now, more of this, I would like to talk about the range. Now, range is something that like confuses us a lot. So now one of the thing is that, let's say if you're finding the range for square root function or square root function, let's say. Now, remember that, let's say if I've got a function, let's say here is the function, and we are asked to draw a square root function for this. So we all know that generally, like, square root of x graph has the range of y greater than or equals to 0, because square root of x graph is like this. But it will be interesting to actually weigh against what exactly we're doing in this. Now, square root of this is a function, and I want to find a square root of this function. So obviously, this part you notice that for these y values which are negative, my function will be undefined. So, and also in the range of the parts where the graph is defined, let's say here, this part which is here and this side, also how do I sketch the square root function? Like, let me take an example, square root of 9 is 3, square root of 11, let's say, is somewhere 3 point something, square root of like 16 is 4. So you see that, like, if you take square root of these y values, you're taking the square root of y values and plotting against the same x values. So square function will be a depleted function, like it will grow slowly compared to the original function. So square root functions are like this. In this case, you can clearly say that, okay, range is y greater than or equals to 0, And domain is, if I pick up this value is -1 and this is 4, domain is x greater than 4 or equal to 4 and or x less than or equals to -1. So you can do that from the graph itself. One of the question, which is an IB exam question that was assessed in May 2021, was this question: find out the domain for 3x plus 2 over x minus 5. So when I'm finding out the domain for square of 3x plus 2 over x minus 5, now look, this is a rational function, and then there is a square root function. Now, if I have a clear idea about how to graph this inside function, it makes a lot of things easier for us. So now I'm going to explain this with two approaches. Obviously, one with the Sine diagram, because if I pick up this function, it must be this must be positive. So you draw the Sine diagram for the roots and the vertical asymptote. So if I put a value here, you notice this is positive. Like here, if I plug in a value, let's say 0, you see this negative, and here again you take a positive. So you can see the domain is x greater than 5 and x less than -2/3. But actually, if you look at the graph part of it, if we have a graph, let's say at x equals to 5, if I have a graph of asymptote here, y equals to 3 is the horizontal asymptote, and then obviously you know how to find the horizontal asymptote by just taking the coefficients. I mean, that's a lame way. Like simple, we know how to take the ratios. Just to recollect that if the degree of numerator is equal, then only you can do that. Like for example, it was 3x squared or x squared minus 5, then also it is going to be the coefficient as 3. But if the degree of numerator is bigger, in that case, there will be oblique asymptote. And if degree of numerator is smaller, you know that x-axis is the horizontal asymptote. So like for example, 3 upon 5 x squared plus 4, this will have x-axis the horizontal asymptote. So in this case, obviously graph is here approximately, and your roots are at -2/3 here, and -2/5 is the y-intercept also. So your graph in this side, it is going to be like this, and here it is like this. So when I'm sketching now the square root function for this, now what is interesting is how well you understand what exactly square root function does. So square root function doesn't give the output for negative y values, obviously here, because you're plotting the y value of this function in the square root. In this case, let's say these are the y values, they become lesser steeper, obviously they grow slowly. And this side, now y equals to 3 was horizontal asymptote, y equals to √3 will become the horizontal asymptote for the resulting function. And this side, it will become a little down, but still the nature is the same. So you can clearly see that y is greater than or equals to 0, but y should not be square root of 3. And a lot of students did make this mistake. They could write y is greater than or equals to 0, but they did not write y equals to negative, or y should not be √3, and that's why they lost the marks. So this is about the basic, interpretation, understanding the log concepts, like log domains, that where it should be positive, how to apply the two functions and look at the intersection for the domains. So one of the questions that is really impressive and really good is this particular question. Let's say if I have got a function x squared plus 4x plus, let's say, 8 upon, or let's say I'm taking this question as little more clearer, x squared plus 4x plus 4 upon x plus 3. And I wanted to find out the domain and range for this particular function without using, let's say, calculus, or without using any particular technology. So first thing is that you look at this function. It is a rational function. It is so x belongs to real numbers. You can say x should not be -3. But now the next part is basically how do I tackle for the range? Now for range for such functions, I mean, we can either graph them with our best mind, but still we can't get the exact y value. So for getting the range in this case, what you can do is you can actually convert this into the implicit relation. So this becomes x squared plus 4x plus 4 equals to xy plus 3y. Then you bring in x squared plus 4x plus 4x minus xy plus 4 minus 3y equals to 0. So you get x squared plus 4 minus x times y plus, don't do this, make x the subject, sorry, this is wrong. So it'll be 4 minus y times x plus 4 minus 3y equals to 0. Now I do b square minus 4ac, b square minus 4ac equals to 0. So it'll become 4 minus y the whole square minus 4 times 1 times 4 minus 3y. Okay, this should be greater than 0 because in case if x and y are real, this quadratic should have a distinct root or equal root. So you get 16 minus, let's say 2y, minus 16 minus 8y plus y squared minus 16 and plus 12y greater than 0. Positive 16, negative 16 cancel. You get y squared plus 4y greater than 0. You draw the Sine diagram, 0 and negative 4. So negative 4 here, 0 here. You take negative here, you take positive here, and you take positive here. So you can see that y is greater than 0 or equals to 0, and y is less or equals to negative 4. So this is basically the general particular, like, range for this function. So when you get a rational function and you don't know the particular, like, range for, mainly in form of where you have got an oblique asymptote. Just to recap how to find oblique asymptote, obviously you do x squared plus 4x plus 4 and long divide with, let's say, x plus 3, and whatever is this quotient that you get is basically the oblique asymptote. So just recapping around that area. And so yeah, so I think this is more of the domain part, like domain, like, key concepts that they assess. Okay, so just touching base upon once again the concept of inverse, like, for some of the complicated functions. So let's say if I have got a function which is f of x is, let's say x upon x squared plus 4. Suppose this is the function. And I'm going to take a parallel example where we also do some sketching for, like, oblique asymptote and all. So let's say I have got a function where x squared plus 3x plus 2 upon x plus, let's say, x squared plus 3x plus 2 upon x minus 3. For these two functions, I'm looking at, like, an opportunity to firstly graph them, and as far as not using technology, and also state their domain range, state in what different ways we can make the inverse happen, inverse exist. So let us first take this example. So I can say that f of x is, in this case, you can see clearly that there is no vertical asymptote. So f of x equals to 0 when x is 0. So the origin is a root. Also, y-intercept is 0. It means the graph passes through the origin. So x is 0, y is 0. Vertical asymptote, x squared plus 4 does not exist. X squared plus 4 can't be 0. And let's draw the Sine diagram. When you draw the Sine diagram here, you can see that this side, if I take any value apart from 0, the denominator does not have any root. So if I take anything beyond 0, you see here it is positive. So if I take, let's say, 1, it is coming positive. If I take this side, it's coming negative. For horizontal asymptote, we know that this is having degree of numerator lower than degree of denominator. So y equals to, let's say, 0 will become the horizontal asymptote. So just to sketch this graph approximately. So when you're sketching this graph, now it passes through origin. That's only clue that we have, since it is passing through origin. So obviously it will be this side, it is going, it will attain a maximum and then come down. This side it is something like this. So here it is, like, obviously you can see that this is a function with, like, unknown maximum or minimum. So generally you find that using calculator, and, like, this is very important to know how to do manually as well as through calculator. But right now I'm going to do is we'll use the technology for this part, to at least a graph. So once again here, let's say if we are asked to calculate the inverse for this particular function. Now, obviously the function is not one-to-one. We can clearly see that this is not one-to-one. So let's say they say that for x greater than or equals to a such that it is the largest domain, find out the inverse, like, where it is meaningful and defined. So obviously in this case, if you look at, we have got like, this part of the graph where I can just take the bar graph and remaining parts I can basically cut down. So this part if I remove, so the function become one-to-one. So if I take function greater than or equals to 2, then its inverse exists. Now for this particular domain, let's see if I have to find the inverse of this function. So it'll become y equals to x upon x squared plus 4. Now when I find out the inverse for this function, it is basically, I would recommend that do with the quadratic formula. So interchange x with y. So y upon y squared plus 4. So become xy squared plus 4x equals to y. So xy squared plus 4x minus y equals to 0. So now after this, we get xy squared minus y plus 4x is 0. So treat x like a constant, and then you can apply in the quadratic formula. So y is going to be negative b, which is 1 plus or minus root b squared. So 1 squared minus 4 times x times 4x upon 2 times x. So it'll be y equals to 1 plus or minus 1 minus 16x squared upon 2x we get. So this is the, like, possible inverses. Now out of these two, one of the, or these we have to choose. So since we are taking the right side of the vertex, we take the inverse as 1 plus the root of 1 minus 16x squared upon 2x. So that's how you find the inverse in such particular case. So now this next question that they can ask you, what's the domain for the function that you calculated? So remember, the domain for function becomes its range for its inverse. So in this case, since my domain was x greater than 2, the range become now for this particular function, it become y greater than or equals to 2. In this case, my range was y less than 1/4 and greater than 0. In my next case, will become x will become between 0 and 1/4 as the so 0 will not be included because it's not going to be counted, like it's going to be a asymptote here. But in this case, this is how you do, particularly like inverting. So if you sketch across y equals to x line, this is how you get this particular part as an inverse. So yeah, so this is like how you do the inverse of rational functions. Try to get them in implicit form, do the quadratic formula, and try to get the inverse. Okay, so all the key concept of functions now, function composition, firstly let's discuss before we start this problem. So as we know that f of g of x, obviously you know how to find the expression and all, but just to understand the more mechanical part of the, like, finding out the composite function. Now for f of g of x to be defined, as we know that range of G must be the subset of domain of F. So range of G, it should be in domain of F. That's a very important criteria. And if it is defined, if this situation holds true, then the domain of f of g of x is going to be same as domain of G. That's number one. Now, in certain cases, you will notice that you have to restrict the domain and range. Of course, I'm not going to do all of those right now. It's just recollecting the criterion. So let's just kind of do the A part. Now, here we have been given a function f of x whose domain is from -3 to 5, and the range is from 1 to -1. And there is another function u of x is x minus 3 and v of x is 2x. We have to state the range for the function u of f. You have to state the range of the function u of f. Now, look, when you see function f is acting like the y values of that function is acting like a x value for u. Now, u of x is this function, which is x minus 3, which is a linear function. x minus 3 is this function. This is your y equals to u of x. Cutting here at -3, we all know that. Now, here the range of this function is from -1 to 1. So basically, you're inputting the value of y from -1 to 1. So if I take x as -1, y value is going to be definitely like -4. If I take x as +1, if I take x as +1 somewhere here, let's say y value is going to be -2. So in this case, the range of u of f that you have is basically y between -2, -4 to +2. So that's the range of the first part. Now, they're asking about the range of u of v of f now. To find out the range for u of v of f, so firstly, when you're finding v of f function, the v of f, now range of v of f will become -2 to 2, because as we just did, when you plug in x as -1 here, because my f takes the value from -1 to 1, so the range of f is becoming like a domain for v. And if we do that here, it is from -2 to 2. Now, I'm going to plug this value -2 to 2 as the domain for u now. So if you plug x as -2 here, you're going to get -5. And if I plug x as 2 here, I'm going to get -1. So the range of this will be -5 to -1. Next part is you have to find out the largest possible domain for f of v of u. Now, f of v of u is a function. If you see f of v of u, now f can take the values only from -3 to 5. It means that v of u function, whatever is the range of that function, it should be between -3 to 5. So first you find out v of u. So v of u will be 2 times x minus 3. So you input this out here. And now this must be between -3 to +5. So if you basically divide by 2 all the numbers, it will be -3 by 2, x minus 3, and 5 by 2. And now you add 3 to everywhere. So look at -3 by 2 plus 3x and 5 by 2 plus 3. So this becomes 3 by 2 and x between 11 by 2. So this will be the domain for the f of v of u function. Next part is explain why f does not have an inverse. Now, obviously, we just discussed that to have the inverse, the function must be 1 to 1. So it should be either increasing or it should be purely decreasing. Now, since you can see clearly the function is failing the horizontal line test, it's not 1 to 1 function. Hence, inverse won't exist. Now, the next part is the domain of f is restricted such that g has gotten an inverse. State the possible largest domain. Now, see, I can restrict the domain. I can cut down this part of the graph entirely, and I can take only this part, which is not the largest, of course. Similarly, I could do from here to here and restrict this part. But the largest domain you can clearly see is from -1 until 3. So if you got -1 to 3, this is the largest domain that you're taking. Now, obviously, that needs to be justified. Now, next is sketch the inverse and the original function on the same graph. So if you sketch it, it is something like here. And so this part will be like this. So the range of this will now go until 3 here. And this will be basically from -1. So yeah, so I think this is how you do this particular like A and B subparts. So the first part is we have to find out the inverse, that is h inverse x. So let's say y equals to 2x minus 5 over x plus d, that's your function. And to find the inverse, first we interchange x with y, so it'll be 2y minus 5 upon y plus d. So you're going to get xy plus xd equals to 2y minus 5. So bringing the y terms together, so xy plus 2y equals to -xd, -5. And so this is negative, sorry. So it will be y, x minus 2 is -xd, -5. So y is -xd, -5 upon x minus 2. And now, since they have said the next part is it is a self-inverse function, you have to find out what's the value of d such that this happens. Now, self-inverse functions are basically the functions which are actually there. If you find their inverses, they're also the same thing. So a typical example that you can take is like y equals to 1 upon x function is a self-inverse function. So if you, or 4 upon x function is a self-inverse, because if you find the inverse of this, it's the same thing. So since it is same as the original function, I'm going to just equate with 2x minus 5 upon x minus x plus d. So you can see here we have got the compare, like some of you would have opened the bracket, cross multiply, and you don't need to do that. You just need to take the comparison. Here you got minus 5, here you got minus 5, here you got x, here you got x. Here you can see compare, just straight away d is -2. Once you got d as -2, your function now basically becomes properly h of x is 2x minus 5 upon x minus 2. Okay, so x minus 2 is the function. Now, next part we have to find out is you have to find out the expression for k of x. So is such that h of k of x is 2x upon x plus 1. So h of k of x is 2x upon x plus 1. Now this is like your decomposition. So I'll just rewrite the stuff that we have got. So h of x is 2x minus 5 upon x plus 5, x minus 2, that's h of x. Now h of k of x is equals to 2x upon x plus 1. So if you're being given an outer function and you have been given some unknown function that you're substituting, so h of k of x, like here, will become 2 times k of x minus 5 upon k of x minus 2. This should be equals to 2x upon x plus 1, because that's my answer. Now, if I take kx as, let's say, k of x as y or something, so 2y minus 5 upon y minus 2, I just need to solve for y. So 2x upon x plus 1. Cross multiply, you get basically y minus 2 times 2x equals to 2y minus 5 times x plus 1. Open up the bracket, so it will become 2xy minus 4x equals to 2xy again here, and you'll get this part is plus 2y minus 5x and minus 5. So 2xy and this get cancelled, and now if you bring in everything one side, you'll get negative 4x plus 5x plus 5 upon 2 equals to y. So you get y as x plus 5 upon 2, which is nothing but k of x is x plus 5 upon 2. So this is like your backwards working, making sure that if you have been given outside function and you want to find the inside function that you would substitute to get the resulting answer, this is the exact procedure that you're going to do. If you want to remember a particular rule that I follow for this, I can give you an additional example on this. Basically, let us say if we have been given a composite function, I'll just take a composite function such as f of x is, let's say, 3x minus 2 and g of x, I don't know, and it has been given, case number 1 is f of g of x has been given as 5x plus 1 upon 3. And what you have to find out is what is the g of x. Now in a case where it is like this, you can always just like do like the previous question. So you just replace g of x here. So f of g of x according to the given equation, it is 3 times g of x minus 2 equals to 5x plus 1 upon 3. So g of x will be 5x plus 1 upon 3 plus 2 and whole thing divided by 3. So you can solve for x now here, you get the answer. What if I had, let's say, g of f of x equals to 5x plus 1 upon 3 instead of f of g of x. So let's say f of x is 3x minus 2. Now, in this case, basically, you have been given like g of 3x minus 2 is equals to 5x plus 1 upon 2. Now, in order to obtain the function, you just got to do is one thing is, you take, let's say, this thing as some variable as y or something, or let's say I take it as t. So you just find the inverse of this function. So let's say t is 3x minus 2. So x will be t plus 2 upon 3. You plug in out here. So g of t you are going to get as 5 times t plus 2 upon 3 plus 1, the whole thing upon 3. And so g of x is going to become, if you replace x here, it will become 5 times x plus 2 upon 3 plus 1 and divided by 3. So this is like a decomposition of function. And this is like, I would say this is one of the method that I taught you. I can give another alternative that you can follow is straight away. If you have been given, I'm just going to clear this out. If you have been given, let's say, a function which is f of g of x equals to h of x. Now this you can remember as a rule. If you have been given an outer function, if you have been given this and you are being asked, okay, to find this. So if you have been given the outside one, g of x is straight away, remember f inverse of h of x. So I'm going to take a simple example for this. Let's say if you got f of g of x as 3x minus 1 and g of and f of x is 4x plus 1. I wanted to find out what is g of x. So now you can see clearly this is like my h of x. So if f of g of x is h of x and I wanted to find g of x, it is simply f inverse of h of x. So I'm going to find the inverse of this function, which is obviously f inverse x is x minus 1 upon 4. Now f inverse of h of x, when you find out, it is going to be obviously like your h of x is this entire function. So it will be 3x minus 1 in place of x minus 1 and whole thing divided by 4. It will be 3x minus 2 upon 4, and that's nothing but your g of x is. So that's about one part. That's how you do the first part. And if you have been given, let's say, f of g of x equals to h of x, you have been given this and you have been given inside and you wanted to find out outside function. Then in this case, it is f of x equals to h of g inverse x. Simply remember that. So f of x will be h of g inverse x. So in that case, you find the inverse of this given function and then do the composition with h. So these are some of the straightforward techniques that can be like, very handy and helpful. So here we have been given f of g of x as x plus 1 and inside is given to us. So f of g of x is, let's say, equals to h of x, and we have been given this, which is x plus 1 upon 2. G of x has been given, and if you want to find out f of x minus 3, in short, first we find out f of x. So f of x in this case is going to be h of g inverse x. Now g inverse x here will be x plus 1 upon 2. So that's a g inverse x. So you're just going to do h of that function. So it'll be x plus 1 upon 2 plus 1 upon 2. So you input basically this out here. Okay, so it'll become x plus 1 plus 2 upon 2 divided by 2, which is x plus 3 upon 4. That's your f of x minus 3. And if I want to find out, f of x, so if I want to find out f of x minus 3, it will be x plus x minus 3 plus 3 upon 4, which is x upon 4. So that's your this particular function. Just to recap the transformations, I'm going to basically touch base upon the core transformations first. Like, obviously we know all of these. F of x is the graph given, and I wanted to do, let's say, the transformations in a way. I wanted to do, let's say, f of x plus a. Now, f of x plus a moves the graph a units up. F of x minus a moves the graph a units down. F of x minus a is a translation vector a and 0, or you can say a units to the right. F of x plus a is basically moving negative translation vector is negative a 0. If you got f of basically ax, it's a horizontal stretch factor by 1 by a. If it is f of x by a, it is hsf, or horizontal dilation by a factor of a. Um, Now, next up is if you got AF of x, it's a vertical stretch factor by A. If you got f of 1 by AF of x, it is a vertical stretch factor by 1 by A. What more interesting is, suppose if you're asked to translate a function according to vector A and B, it simply means nothing apart from f of x minus A plus B. So if it is the function, you will say f of x minus a plus b. That's what is the transformation. Two transformations, which are like your negative of x, it is reflection in x-axis. Reflection in x-axis. F of negative x is reflection in y-axis. Reflection in y-axis. Then we have got absolute value of f of x, obviously, is basically it's going to reflect the parts whichever parts are below x-axis. Okay, so those parts basically get reflected in the x-axis. So like these will be the absolute value. While if you're talking about f of absolute value x, if you have got a function, let's say something like here, if you cut down this part of the graph and reflect the remaining part across the y-axis, this is called as f of absolute value x. Now, just taking this opportunity to kind of recap the transformation or one of the type of basic property of the function is like even odd function. If your f of negative x is f of x, it means that if your function is exact reflection in y-axis, then it is called as even function. But if your function f of negative x is exact negative of the original function, then it is odd function. Odd functions are generally symmetric about origin, and these functions are symmetric about y-axis. And f of absolute value function is always an even function because it is always going to be symmetrical about y-axis. Suppose if you are sketching f of absolute value for this is how it's going to be. So f of absolute value x is always symmetric about the y-axis. So now what is really important is that what are the kind of question that we can get as like in the category of challenging question. Now I'm going to take a question that kind of covers and basically like we can do almost everything in that. Suppose if you got a function f of x is, let's say, 3 plus 2x upon x minus 5. And the first question is you got to sketch this and state the VA, SA, HA, and so on. So when you have a vertical asymptote, let's say x equals to 5, horizontal asymptote is y equals to 2. Second is the roots when you're taking as x is -3/2. Then third part is if you take the y-intercept, which is basically when you plug x as 0, y is 3/5. So your final graph when you sketch actually is going to be like this. So here it is like the final graph. I'll just redraw this. So let's say this is my x and y axis. Now we got the vertical asymptote at x equals to 5, and horizontal asymptote is x equals to y equals to 2, and then you got the roots as -3/2, roots as -3/2 here, and y-intercept is -3/5. So basically your function here is this part is like this. In this part it is going to be down, and here this part of the function is something like this. So this is basically the graph of this function. Okay, now next part that they can ask us is like, linking up a little bit with the transformation that we just did, is using your graph, could you solve, let's say, f of absolute value x is, let's say, less than 2. Solve f of absolute value x less than, let's say, 2, or f of absolute value of x less than 1, or something like that. So they can ask you that. So let me just tell you firstly, you're going to draw an absolute value graph. So you're going to draw the absolute value, which means that you're going to cut this side of the graph. Okay, and then you're going to reflect the remaining part in y-axis. So it was something like here. So you're going to get like this. So you have this as basically the f of absolute value. Now, if you're solving, where is it less than 2? Obviously, you draw y equals to 2 line, which is already drawn as asymptote. You can clearly see it is between these 2 points. Like between these 2 values, the function is below y equals to 2. So your correct answer for this question, is x should be between -3/2 to positive. No, this will become x equals to 5. Sorry, -5. Because this asymptote also disappears. So you will have a proper symmetrical graph. So this will be -5 to +5. So that's the correct answer. In case if they ask us, okay, solve where is absolute value of f of x greater than or equals to 3. So when I draw y equals to 3 line, obviously, like first you draw absolute value of the graph. So if you draw the absolute value of the graph, it is going to be basically, I'll just erase firstly the original part which I had drawn for the previous question. So this was our original function basically. Here was the x-axis. This was our original graph. Okay, now to draw the absolute value, you just basically going to reflect this out here. And then you draw y equals to, let's say, 3 line. Draw y equals to 3 line here. So if you draw y equals to 3 line in this case, it is, your graph is basically going to be, this is the part which is they're asking for. So you just got to get the intersections. So for this intersection, you're going to equate the negative of this function, because this part is reflection x-axis. So you just equate the negative of the function. So negative of 3 plus 2x upon x minus 5 equate to positive 3. You get this particular intersection. And for this intersection, you equate the original curve, which is 3 plus 2x upon x minus 5 equals to positive 3. So could you just make sure that you solve this properly? So final answer for this will be basically when you solve this, you get x as 12 and 5, or x as, if you solve this equation for this intersection, you get x as 18. Now you can see that this is entirely above in this, this range apart from x equals to 5. So you can see that obviously x should be between 12 over 5 and 2, or 12 over 5 to 18, but x should not be 5 because there is a vertical ascent at that point. That will be the answer for this particular question. Now, what is more interesting is that they can ask you to write down this question in a format of, let's say I'll just erase this part. If they ask us to write down this in y equals to a plus b over x minus 5, and hence tell what transformation map 1 upon x onto 3 plus 2x upon x minus 5. So you have got multiple techniques for this. You could just do the long division, like 2x plus 3, you did take here x minus 5, 2x minus 10, here we gone, this is 13. So you get this answer as a, the quotient, which is 2 plus 13 over x minus 5. So you get this part. Now you can clearly see, first I'm going to vertical stretch 1 by x function, vertical stretch factor, vertical stretch by 13. So you get 13 by x. Then you move the graph by translation vector 5 and 2. So move the graph 5 units to the right and 2 units up. And you are supposed to do these kind of questions with confidence. You're supposed to know these things very clearly, because these are very important stuff in the function transformation. Now this is basically the reciprocal function where already you can see the existing vertical asymptotes and there is a horizontal asymptote. So let me just brief you firstly certain rules of the reciprocal function. So obviously, like as we know, the vertical asymptotes and becomes roots, and roots become asymptote. So it means that if you've got a function already with a vertical asymptote, that converts to root, and if there is a root already, it becomes a vertical asymptote. Okay, if a function is increasing, the reciprocal should decrease. If a function has a minimum value, the reciprocal have a maximum value. If a function has a maximum value, reciprocal is going to have a minimum value. So basically in this case, you will have this as a vertical asymptote, this as a vertical asymptote, this 2 becomes the roots because they are already vertical asymptotes. There is a maximum point here that becomes the minimum point at -12. It comes here. So this side, you can see clearly the graph is something like this. This side, the function is going to be like this, down, it is going to go down. Here, if you got a function like with a horizontal asymptote already, its reciprocal will be also the same because y equals to 1, if you take reciprocal of that, it will become y equals to 1 itself. If I have got y equals to 2, but in that case, your horizontal asymptote will become y equals to 1 by 2. This side, you can see the minimum value it was approaching was 2, 1. In reciprocal function, the maximum value will approach is 1. So the function is approaching the horizontal asymptote from top, reciprocal will approach the same reciprocal of the horizontal asymptote from bottom. And this side, as you can see here, it is a vertical asymptote. It should be coming from infinity. And this side, it will come like this. So this is how you do the reciprocal function for this particular question. So now when you're sketching the square function, so since you're sketching square function, you're basically mapping x against f of x the whole square. So basically, now remember that wherever your function like y is, let's say 2, those will become y equals to 4. Now, if there is a vertical asymptote, that doesn't change, that will remain vertical asymptote. If you have a function y value which is between 0 and 1, it will be, if you square, like for example, a y value is half, if I square, it will become 1/4. So in that case, if you see y equals to, firstly, y equals to 1 is an invariant point and y equals to 0 is an invariant point. Now, if you square a function value between 0 and 1, then in that case, your square function will come closer to the x-axis. So in this case, this side, the graph will be here. And then after that, it will shoot up and will approach y equals to 4 line. Here, it is obviously the same stuff. In this case, it will be something like this, asymptote to this. And y equals to 4 here, you'll see a graph like this, square function. Now for the second one, once again here, invariant point is 0 and 1. So you draw y equals to 1 line. In between the function, it is graph is going to be like this. Here it is going to be something at 1,9, and then it will be something like this. So this is the graph of this part. So this will be 1,9. But now if I move 1 unit up, so this obviously the new graph position is going to be something here. And yeah, so this is the squared function. So yeah, so I hope this is helpful.